Hello friends, in our previous lecture or previous chapter, we discuss about the motion and their types. Also we discuss about the speed and velocity, distance, displacement, also acceleration, their types, velocity, their types, inertia, the concept of inertia, and mainly the Newton laws of motion, Newton's second law, Newton's third law, which is action reaction. Also the pseudo force and the four fundamental forces. In this chapter, we only check that the change in that motion of object which it depends on the force acting on that object. So if you apply the force, then this only changing their position. But this force, or we can say that how long the force which act on that body. So in this chapter, if you consider the force into time, or basically the impulse. So the quantity force into time, which is nothing but the impulse. So basically we have to change or check the force, which is how much long acts this force. So if you considering the time or this quantity force into time, you get the impulse, or you can say that the impact. So if you apply the force with respect to time, this body or this object will be changing with position, changing their position with time. But again here it's the how long not always mean that time. So again we have to check if you apply the force and this object changing their position, we can say that distance, the quantity force into distance. So if you apply the force on that object, this object covers some distance. So on that application of that force, this object covers some distance. So in that case, we can say that the work done by that force. Here, here we can say that this force, we can say that this force makes some work done on that object, on that body. So in the chapter we have to discuss it totally the work and energy. So this force which is changing their positions, so how much distance will be covered, how much distance will be covered in the application of this force, and this basically this object changing their position in that in which direction, so which is in the direction of applied force. This is in the direction, in which direction, which is in the direction of applied force. So you can say that the work is done here. This work, we can defining the definition of this work. When we say the work is done, so if the work is done on that object, if you are acting the force, if this force is acting on that body, and this body will be cover some distance and in that direction of applied force. So in that case we can say that the object, or we can say that this object or force will make the work done. Here we just look at some simple examples for the work done. So as per our simple definitions, just consider the football ground. In that football, when you kick the football, then here also you apply the some force, and as per your force and also the directions, so when you click the football, then this ball will be changing their position, or we can just say that this ball covers some distance. So when you apply the larger force, then this ball will be cover the larger place or large distance, or also this force will be less. In that condition, it covers the small distance. So from there we can say that the work will be done on that ball. So the player will be make a work done on that ball. So here this force, it applies the force, and this ball which cover distance. Even we can take the example as a bowler. So in cricket we can see that when bowler throw the ball, and in that conditions we can see that when it throw the ball, it gives the force, and as when he give the force in that conditions, this ball will be cover the distance, and which gives the, when it release or leave from the hand, then it cover from non-striker end to the striker end. Also when this moving ball hit on the some wall, so we just throw the ball, when this ball will be hit on the wall, in that condition from this wall is another body, so it applies the force on that body, due to which it get from this place. So here also this work done by that ball. Now, so there is simple one more thing is that, so the capacity of that ball or the body which to do the work, here we can say that basically it is nothing but the energy. So the capacity of the body, or sorry, capacity of that ball or the body to do the work. In same case in the football also, so the capacity to do the work by that ball or the body, which is nothing but we can say that the energy. Here we can say that energy. So this is one more concept. So how much speed, how much, not a speed, how much force we apply, how much your capacity to hit that ball, to kick that ball. So here we can say that it is basically nothing but the energy. So the energy of that body is basically defined by the capacity to do the work. Simply we can say that the capacity to do the work. So energy, which is nothing but capacity to do the work. This is our simple basic definition of that energy. This energy is divided by, or it having the various types. We can say that this energy is found in the form of heat, in the form of light, in the form of sound also, or in the mechanical energy. So we are interested in the mechanical energy, and this mechanical energy which is divided by, again in two types. So one is kinetic energy and second is potential energy. So here we are interested in the mechanical energy. This mechanical energy which is having a two type, kinetic energy and potential energy. Now we are interested in what is mean by the kinetic energy. So the simple definition is that the energy possessed by the body, this energy possessed by the body by virtue of, okay, this energy which is possessed by a body by the virtue of its motion. Important thing is that motion. So it is simple definition. This energy which is possessed by the body by virtue of its motion. It is nothing but your kinetic energy. When you say this, basically when any object in the motion, when you apply the force, when you apply the force of the body, then this body get in the motions. And if this body is in the motion, we can say that this energy which possessed by the body to virtue for this motion. So this basically this kinetic energy, again it's a scalar quantity. Here we are considering scalar quantity. So it's having only the magnitude. Here we are not considering the direction. Here we are considering only the magnitude. Hence it is only a scalar quantity. And we are if you considering the unit of that energy, again this is the unit of simply the work done. So we have unit which is nothing but the joule, which is having the work done in your SI system, and the earth which is in CGS system. In SI, your work which is having the unit is same joule, and the earth in your CGS system same unit for your kinetic energy. And this kinetic energy is a scalar quantity, and its simple definition is the energy possessed by the body by virtue of its motion. It means its velocity. So here this kinetic energy depends of that particle of that body is depends on the velocity. Is depends on a velocity component. So we are defining it's the velocity of particle changes here in this condition or in this example in your kinetic energy, which is depends on this velocity. If the velocity of that particle changes, so by applying the force, when you at what condition your velocity changes? When you apply the force, any particle object which is at the rest get in the motion, it means that their velocity, they are applying force which changes, then their velocity changes. This velocity, this kinetic energy depends on this velocity, it means your kinetic energy also changes. So here by apply that force, which change, if you changes this applying force, change in the velocity, and by naturally the kinetic energy also changes. So here we are considering small example or small derivation. To solve this kinetic energy or check the simple equation of that kinetic energy, we are considering a particle which is having a mass m. We are consider particle which is having a mass m, and this particle moving with a velocity v, which is moving with a velocity v. So you get the relation, or by definition this kinetic energy. Here we can say that the energy possessed by the body by virtue of its motion. So which is nothing but 1/2 mv square. It is 1/2 mv square, or we can write 1/2 mv dot v square. Multiplication of simple velocity, or we can write simply this 1/2 mv square. Here you get this kinetic energy depends on that velocity. This velocity basically when changes, when you change the applied force. If you change this applied force, this velocity changes. This velocity changes, it means that our kinetic energy of that particle also changes. So here we have to check the relation between the force and velocity. Here we have to check simply in all the condition the applying force, which is if it is a tangential, if it is a perpendicular, what you get? Can you get this motion? What about the relation between this force and velocity? So to check that condition, we have to differentiate this equation. So we have differentiate with respect to time. Then you get dk by dt, which is equal to again v into m dv by dt, which is nothing but dv by dt. Or simply here also we can get, simply this is also from this equation also we can write, you know that twice here 1/2 mv into dv by dt. Okay, this is just we differentiate this velocity or this kinetic energy with respect to t, then this is 1/2 m d by dt of p square, and this d by dt of p square is nothing but twice p dv by dt. So here these two cancel, you get mv dv by dt. It is a simple relation. So again you know that the Newton's second law. So this Newton's second law is simply the basic relation between your force, mass and the acceleration. It is simply the relation between force, mass and acceleration. You can write F is equal to ma. You can write F is equal to ma. This a is nothing but the acceleration. Acceleration is nothing but simply we can write m, the rate of change of your velocity. So here you get dv by dt. This acceleration, which is nothing but the rate of change of velocity. So we can write F is equal to m dv by dt. So here again we get this. You can put this value of the force in your equations. So this m dv by dt, in that place we can write F. So you get here this dk by dt, which is nothing but this p, and instead of m dv by dt we are writing F. So p dot F, here this v dot F, the rate of change of this kinetic energy dk by dt, which is equal to p dot F. So we are, if considering the dot product, here we can write p F cos theta. Here you get simply, this is your dot product, velocity into dot force, you can write p F cos theta. Now this theta, where this theta is an angle in which the tangential force we are applying that force into that velocity. This angle, this theta, basically the angle between applying force and that velocity. So now from this equation, from this dk by dt, from this equation dk by dt, which is nothing but pf into cos theta, basically in that equation you can see that the kinetic energy of that body which changes if the speed it changes. Here we can see that if the speed changes, then your kinetic energy of that body which is also changes, and it happens when it is happened when this acting force or the force which is acting on that particle which is the tangential. Here in that conditional, when this force, if this force is in the tangential component, then and then only the speed of that object, of that particle will be changes. And if this force is perpendicular, now here we can see that if we are considering, okay, I am leaving all these things and simply considering dk by dt, which is nothing but p dot f, which is nothing but pf cos of theta. This theta, which is the angle between this applying force and velocity. So now if we are consider, okay, so we are considering any object or the particle, if you apply the force tangential and perpendicular. Okay, so in first case we are just considering, we are applying the force in horizontal directions or in a tangential component. Then this theta is equal to 0, and if this theta is equal to 0, your cos theta is equal to 1. Here cos theta, which is equal to 1, and you get this df, here this dk by dt for that condition. For theta is equal to 0, you get you get dk by dt, which is equal to p into f. So it is basically product of your velocity and applying force. And if you consider this applying force is in the perpendicular direction. Now here if you apply the force in the perpendicular direction, so in that condition this theta is equal to 90 degree, and if this theta is in the 90 degree, your cos theta become a 0, and this dk by dt or change in the kinetic and change in the basic kinetic energy become a 0. So in that condition, when this applying force is in the perpendicular directions, then the kinetic energy of that particle does not change. This dk by dt, which is equal to 0, it means that if applying force is perpendicular, this change in the kinetic energy is 0. Or we can say that here also we are say that in the form of work done. We are explaining in the form of work done when this F and W are perpendicular. Sorry, F and P is perpendicular to each other for all the time. Then the work done. We are defining the work done. So if you apply the force, then if you apply the force on any particle, in that condition it displaces from some distance. So basically it is applying force. This work done is equal to applying force into some displacement, which is nothing but ds. So which is nothing but f dot dv. Sorry, f dot p into dt. So at any small time interval, in that f dot p into small time interval dt. So this f is perpendicular to p. In that condition, this time interval is basically we can found 0. Here this f is perpendicular to v. So in that condition we just see that the kinetic energy does not change. So for that we check simple one example. Just consider the particle which is moving along a circular path. When it just connecting, just consider take a string, and the one that string which is having a length L, and it's other end of that string which is fixed. So in that conditions, in that kinetic string, so in that conditions when you apply the tension to that string which is always perpendicular. So if you considering the one end of that string is nothing but, so if you considering the one string which is length having L, one end is a fixed, another we are rotating. So in that circular path, this tension of that string, the tension of that string which is always perpendicular to the velocity. So tension is always perpendicular to velocity. So in that conditions the kinetic energy does not change. So in this example again we can see that the tension in that string, so here work done is 0, here the work done, because of this tension is perpendicular to v, so here applying this force which is perpendicular to the velocity, hence this work done is 0. You get the work done is 0, and this work done is 0, it means that the kinetic energy remains constant. So the kinetic energy remains constant. So in that simple example you can check your work done is 0 just because of the tension, which is nothing but one type of force which is perpendicular to that velocity, and hence this work done is 0, and this work done is 0 shows that the change in that kinetic energy or simply kinetic energy is of that particle which is remains